In this example, we are going to look at the application of the local max, local min, or the local extrema for functions of two variables. The owner of a store advertises on the television and in a newspaper. He has found that the number of units that he sells is approximated by the function n of xy equals 0.1 x squared minus 0.5 y squared plus 3x plus 4y plus 400, where x in thousands of dollars is the amount spent on television advertising, and y in thousands of dollars is the amount spent on newspaper advertising. How much should he spend on each to maximize the number of units sold? That means we are going to look for the value of x and y that optimize or maximize the number of units, or that the one that gives you the local maximum value. So we are going to use the b-test. By the first step, find the critical point. It could be more than one point. We'll find out. To find the critical point, first partial derivative with respect to x equals 0. First partial derivative with respect to y equals 0. And we're going to solve for x and y that satisfy these two equations. And then for the second part, we're going to compute the d value or the d quantity using the second partial derivative with respect to x times the second partial derivative with respect to y minus the second partial derivative with respect to x with respect to y quantity squared, and compute at the critical point that we derive from computing in the first part. So this one, we're going to solve for the point A, B. Let's get started. To find the critical point, from the function, we find the partial derivative with respect to x. We'll get negative 0.2 times x plus 3. The first partial derivative with respect to y, we will get negative 1 times y plus 4. And let both of them be 0 and solve for x and y. That's nice that the first equation involving x alone, so get x equals negative 3 divided by negative 0.2, or it turns out to be 15, and y equals negative 4. Now we got the order pair that we call the critical point. So 15, negative 4. Next, we are going to compute the quantity d using the second partial derivative with respect to x and the second partial derivative with respect to y, together with the second partial derivative with respect to both x and y. So for the second partial derivative with respect to x, we get negative 0.2. Second partial derivative with respect to y, we get negative 1. And the second partial derivative with respect to x with respect to y, we will get 0. Then for the quantity d equals negative 0.2 times negative 1 minus 0 quantity squared, and gives us a 0.2. That is greater than 0. If it is greater than 0, that means the point that we found, the 15.4, would give us either local max or local min. So we're gonna do further by consider the second partial derivative with respect to x. In this case, it's negative 0.2, which is less than 0. With these two conditions, we can say that the point 15.4 will give the local maximum. The problem doesn't ask for the value of the local maximum. We just look for the points or the x, y value that gives the local max for this case. So we derive the answer 15.4. We say x equals 15, a unit in 1,000. and Y is for unit in thousand as well. That's spent on the advertising, or we can put in as 15,000 and 4,000 respectively.